Welcome to Engineering Studio with Dr. Mohammad Tahir. In the previous video, we have studied the concept of shear in case of two-way slabs. We have studied what is one-way shear and two-way shear or punching shear, and we have also studied the different types of two-way shear. In this video, we are going to solve one example to check for the punching shear if the punching shear of the slab is sufficient or we need to provide some shear reinforcement inside the slab to resist the punching shear. The problem is perform check for the punching shear of two-way slab system at the given edge column. So we have given a edge column out of a two-way slab system. The panel size is 6 meter by 8 meter. So the panel for which this edge column is shown, it is 6 by 8 meter. And all conditions of the direct design method are satisfied. So we are assuming that the direct design method can be used to design this slab system. The other related data is as under. The applied load is the applied factor load is 11,000 Pascal Newton per meter square. Mu unbalanced moment at this column is 200 kilonewton per meter. Fc prime is 25 megapascal. H, the thickness of slab is 230 millimeter and the effective depth of the slab is 190 millimeter. And here in this figure we have been given that the center to center dimension of the panel is 8 meter in this direction, and in this direction the total span is 6 meter and the half span will be 3 meter plus. So up to this much distance, up to the center of this column, it will be 3 meter, and the width of column is 600 millimeter. So half of it will be 300 millimeter, and we have projection of slab equal to 200 millimeter. So overall width will be equal to 3.5 from the edge of the slab up to the center line of the panel. Okay. So to solve this example, we need to satisfy this equation, that whether this applied shear stress is less than equal to phi Vc or not. If it is less than, then okay. Otherwise, we need to design the reinforcement. So we need to check this, whether it is okay or not. Okay, so there are different approaches to calculate this. So first we can calculate this resistive shear. So how much is the resistive shear for this slab system or for this slab? So here phi will be equal to 0.75, which is in case of slabs, and Vc we can calculate by using three equations, and these three equations are given over here. These three equations here: lambda, beta and Fc prime. So beta is actually the ratio of longer to shorter side of the column. For example, if in our case the longer side of the column is 1200 and the shorter side is 600, so it will be equal to, here it is calculated. So beta is longer to shorter side ratio of the column. So it is actually 1200 divided by 600. So it will be equal to 2. So this beta is equal to 2. Okay, next in this equation we have lambda factor and its value is 1. So we can calculate the Vc value from here. So if we substitute these values, so lambda 1, 0.17 times 1 into 1 plus 2 over beta is also 2 and square root Fc prime, and Fc prime is 25. So it will give this value, and in second case alpha s. So in case of edge column, the alpha s value is 30 and d is 190, it is given. B naught. So we need to calculate the dimensions of the perimeter. So in that case, if we see, the perimeter will be on three sides. So we will have perimeter in these three sides. So here if I see in this side, so it will be equal to 200 plus 600 plus d by 2. From this face of this column it will be d by 2, and d is 190. So it will be 190 divided by 2. Okay, so in this direction, if we calculate this perimeter value or the dimension of the perimeter in this direction, so here it is d by 2, so 190 by 2 plus this dimension of the column 1200 plus this d by 2, 190 by 2. So here we can calculate this dimension in this direction. So this is B2 and this is B1. So in the next slide we can see how they have calculated. So for B1 in east-west direction, so it is 600. We have column like this, 600 and 1200. So this will be the situation. So 600 column dimension, 190 by 2 this dimension, d by 2, and 200 the extension of the slab from face of the column. So it will be 895. And in case of B2, this dimension, it will be 1200 the dimension of column plus d by 2 from this side and d by 2 from this side. So it will be equal to d. So it is 1390 millimeter. So if we want to calculate its parameter, so it will be this. Only we need to consider 3 sides. So 2 sides for B1 and 1 side for B2. So 2 times beta 1 plus B2. So it will give us 3180 millimeter, 3.18 meter. And alpha is, we have already seen that it is 30 in case of H column. Okay, so we need to substitute the value of B0, which is 3180. So after substituting these values, alpha S and B0 D, we will get this value 1.574. And similarly here 0.33 lambda FC prime, so its value is 165. So we need to consider the least value. So out of these three, this one is the least value, 1.574. So our design strength will be equal to 0.75 times 1.574. So 1.181 will be our design compressive strength, or the capacity of the slab to resist the shear capacity of the slab. Okay, next our task is to calculate this applied shear VU, which is equal to VU applied shear divided by AC plus minus MUV C over JC. So here first we can calculate this AC value, the area of the parameter. So it will be area of the critical section. So it will be B naught time D, parameter of the critical section, time the depth of effective depth of slab. So this much area will be resisting the applied shear. Okay, for VU we have already seen the formula, which is equal to length and width minus B1 into B2. So if we have column over here, so if this is critical section, so this much area will be causing this direct shear. So from here to here it is length and this much is width, minus we need to subtract this B1 times this B2. So length into width minus B1 times B2. And QU is the applied load, which is given in Pascal. So it is given in Pascal, Newton per meter square. So we need to substitute these values, length and width, in meters as well, because this 11,000 is in Newton per meter square. And we need to divide it by 1000 to convert it into kilonewton. Otherwise the value will be in newtons. So it gives us 294.3 kilonewton. So this much is the direct shear. So direct shear stress, to calculate the shear stress we need to divide this shear force with the area. So VU divided by area. So here it is in kilonewton and this area is in millimeter square. To convert it into megapascal, we need to convert it into Newton millimeter square. So convert this VU into Newton, so multiply it with 1000 divided by the area. So it will give us the applied shear stress. because of gravity loads. So 0.487 megapascal. So now we need to calculate the eccentric shears. To calculate the eccentric shear, if we see, we need MUV C over JC. So C will be equal to X1. So we need to calculate X1. We need to calculate this JC. And for calculating this MUV, we need to calculate gamma V, which is equal to 1 minus gamma F. So first of all, X1. So X1 we know the formula which we have seen in the previous video, B1 square over 2B1 plus B2 in case of edge column. So by substituting the value, we can get the value of this X1. Similarly, the equation for JC is also given, so we need to just substitute the value of B1, B2 and D. And what is B1 and B2 we have already seen over here. So here it is B1 and B2. So we just need to substitute these values in this equation. So after substituting the value, we can get the value of JC, which is over here. Okay, next is to calculate gamma V. So gamma V is equal to 1 minus gamma F, and gamma F is given by 1 over 1 plus 2 by 3 square root B1 over B2. And B1 and B2 are again the dimensions of the critical section. So we have already calculated, just need to substitute over here. So gamma F is 0.651. So it means 65.1% of the unbalanced moment will be transferred by the direct flexure and remaining 35% will be transferred by the eccentric shear. So for eccentric shear, here it is written gamma V time MU. Actually MUV is equal to gamma V time MU. So instead of MUV, it is written over here gamma V MU. So gamma value, it is 0.349. MU, it is given 200 kilonewton meter. And we have multiplied it with 10 raised to power 6 to convert kilonewton meter into Newton millimeter. We have to multiply it with 10 raised to power 6. And X1 we have calculated in the previous slide, which is 252. Okay. So JC, this is also given, it will have a unit millimeter to power 4. So after substituting the value and calculating it, we will get the value of eccentric shear stress, which is 0.329. And the total applied shear will be equal to VU plus minus VU over AC plus minus MUV C over JC, mean indirect shear and direct shear. So definitely if we subtract, it will give us the low value. So we only need to add these two values to get the maximum applied shear. So this is direct shear and this one is the indirect shear. So if we add these two values, so we get the maximum applied shear, which calls the punching of the slab. So it is 0.815 megapascal. So now we have calculated the total applied shear, and we have also calculated the resistive shear provided by the slab. So now we need to check the design equation. VU should be less than 5 VC. So here VU should be less than equal to 5 VC. So VU is 0.815 and 5 VC is 1.85 or 1.815. So this value is greater than this one, so it is okay. So it means the slab can resist the applied shear without the shear reinforcement. So if this is not true, this is greater than this value, the applied shear is greater than this value, so then we need to provide the shear reinforcement, or we can provide the column capital, or we can go for the drop panels, or the third option, if the difference is very small, then we can increase the thickness of slab. So out of these three different scenarios, we can consider the most suitable. Okay, this is all about the direct design method.